The title of this video will probably no longer be true after this video has been out for a few years and teachers have started actually noticing it, but I'm going to keep it as it is no matter what. Anyway, 7 things your physics teacher never taught you about Newton's third law. Anytime I see a student making a mistake involving Newton's third law, it's usually because they weren't taught about or misunderstood one of these 7 ideas, which I guess I'll call 7 clarifications to Newton's third law, or maybe we can call them 7 corollaries. Yeah, I think the word corollary fits here. But anyway, whatever you want to call them, 7 things you need to know about Newton's third law. Let's start with the actual statement of Newton's third law. So you probably know it since even before physics because you've heard it used in popular media. For every action, there's an equal and opposite reaction. So the first thing that we're supposed to take away from this is that all forces in the universe exist as pairs. No exceptions. Some students might wonder, well then what about a block that's free falling in a vacuum? So there's no air resistance. There can only be one force, the force of gravity pulling down on the block. Where is the second force, they might ask? Doesn't this violate Newton's third law? And the answer is, of course, no, it doesn't. I mean, I would imagine physicists would have caught this a long time ago if it really was a violation, so that's your clue that there is no violation. What's really happening is that the reaction to this downward pull on the block exists somewhere else, somewhere that we're usually not interested in. It acts on the Earth itself. So there's a force of gravity that the Earth exerts on the block. There's a force of gravity upward that the block exerts on the Earth. We usually don't mention it because in a problem involving a block, we're usually concerned with the motion of the block, not the motion of the Earth. So there's that first little mystery solved. Okay, number 2. Action and reaction are not only equal in magnitude, they are also of an equal nature. In other words, they're always the same type of force. So one time I stumbled upon a video on YouTube that really got on my nerves, because in that video they did the following. They drew a block on the ground or on a table, let's say on a table. So I'll draw a little table here. And they started drawing the force body diagram for the block. And they said, okay, there's a force of gravity pulling down on the block. And then there's a normal force upward that pushes up on the block. And it happens to be equal in magnitude to the force of gravity. And the person who made the video said, oh, the normal force is a reaction to the gravitational force. No. Absolutely not. Absolutely not. Equal and opposite reaction. Equal not just in magnitude, but also of an equal nature. The reaction to a gravitational force must be another gravitational force. The reaction to a normal force must be another normal force. So I can give one quick example that quickly debunks this idea of normal force being a reaction to the gravitational force. By the point that you start doing Newton's third law in physics, you should have already seen, at least I would hope you've already seen, examples of inclined planes. So if I have a block on an incline on a ramp, then if you draw out the force body diagram, let's say that this incline is frictionless, just to keep it simple, then you have a force of gravity on the block that pulls it downward, and the normal force is not straight up. The normal force is perpendicular to the incline, perpendicular to the surface. It's this way. So in terms of direction, it's not the exact opposite direction, so on that alone, it can't possibly be a reaction to the force of gravity, but also it's not going to have the same magnitude either. If you've already done this in your physics class, then you probably know that the magnitude of the normal force here is, assuming no other forces are involved, it's going to be equal to the force of gravity times the cosine of the angle of the incline. So yeah, that immediately tells you that something else is going on here. So what's really going on is that this normal force is a reaction to the normal force exerted downward on the table. Table exerts a normal force upward on the block exerts a normal force downward on the table. Earth exerts a gravitational force downward on the block, and as we saw in our previous example, I'll just draw this to represent the Earth. The block exerts a gravitational force upward on the Earth. So that's what's really going on. The reaction to a normal force must be a normal force. The reaction to a gravitational force must be a gravitational force. The reaction to a tension force must be another tension force, etc., etc. Remember that. Number 3. Action and reaction always appear, disappear, increase, or decrease simultaneously. If action and reaction change, they change together. So I guess for this one, I'm not really sure what I can draw for it. Well, I know what I can draw. Just a simple person pushing a box. Let's say we've got a box, and let's say we have a person who's pushing on that box. Let's go with this color. Time to see how good my stick figures are. It's been a while since I've drawn these. Yeah, this person's arms are definitely too long compared to the rest of their body, but we'll ignore that. So, if the person exerts some amount of force on the block, let's say they push on it, but the block doesn't move because there's enough friction to prevent it from moving. So there's a force of friction here, a force of static friction preventing motion, and this person is exerting some sort of applied force forward, and of course the block will apply a force on the person, a reaction to the applied force. If the person starts pushing harder because they couldn't get the block to budge the first time, then of course the pushback that they get from pushing on the block also increases at the same time. You can actually do this at home. Just push on a wall or something, and you can feel this for yourself. Or not even a wall. You can vary the intensity with which you're pressing your foot down against the ground, and you can feel how hard the ground is trying to prop you up based on how intensely you're pushing down your foot on it. So yeah, as soon as you push harder against a wall or against the floor, you immediately feel the floor or wall pushing back against you just as strongly. They increase together, they decrease together, they appear together, they disappear together. It always happens at the same time, which leads us to number 4. Number 4, in a given pair of forces, labeling one of them as the action and the other as the reaction is a completely arbitrary choice. Is this applied force the action, or is it this one? It doesn't matter. It doesn't matter. This applied force is a reaction to this applied force. This applied force is a reaction to this applied force. You have to realize that the word reaction in physics does not mean what it means in everyday life. In everyday life, when we say reaction, that usually means something that happens afterwards, a response, something that has to come after seeing whatever it is you're reacting to. It doesn't mean the same thing in physics. And that shouldn't be too foreign of a concept to you. After all, reaction doesn't mean the same thing in chemistry. A reaction in chemistry is definitely different from a reaction YouTube video, for example. We all know that there's a difference in the meaning based on the context. In the context of physics, the word reaction does not imply that it happens afterwards. They happen at the same time. The word reaction here is just describing how these two forces relate to each other, how a given pair of forces are related in this way that they have opposite direction and equal magnitude all times at the same time. Okay, so that was number 4. So then, this leads us to number 5, probably one of the more common questions, actually. Why is it that when, say, I kick something, I don't get sent flying backwards? So let's say we've got ourselves a soccer player who kicks a ball. Why is it that the ball gets sent flying while the person probably doesn't even get pushed back at all? First of all, a person's motion is going to depend on all the forces acting on them. Motion, if you remember Newton's second law, is determined by net force. Net force determines your acceleration. Net force is what determines your acceleration. Equal and opposite force does not mean equal and opposite motion. You have to consider the net forces, not just the two forces involved in the kick. So if this person kicks the ball, let's say they just kick it completely horizontally to keep things simple, they're going to have some sort of applied force here, which is really just a normal force, but that's a more complicated conversation for later. We'll just call it applied force because it's simpler that way. So those two forces exist, but those aren't the only forces. As for the soccer player, there's probably going to be friction. So I usually like to use these tick marks to indicate that the ground is rough. So there's probably going to be some sort of static friction force preventing their motion. And of course, there are other forces on this person. There's a normal force that the ground exerts upward on them. There's a force of gravity pulling downward on them. And I'm definitely not drawing these to scale, though I probably should be. Let's see. And I guess for the ball, well, if it lifts off the ground a little bit during the kick, then I guess we can ignore the friction on it. But the point is, the applied force on it is going to outweigh any other forces that are pulling back on it. So the net force on the ball is going to be somewhere to the right, while the net force on the person is going to be, well, 0 when you take all the other forces on this person into consideration. So that's one of the reasons, but even in the absence of other forces, there's still not going to be equal and opposite motion. Let's say that this soccer player is in outer space, far away from any planets or whatever. Let's say this person is in outer space, far away from any planets, stars, asteroids, whatever that could exert some sort of gravitational pull on them. In this case, if the person kicks the ball, then there are no other forces except for that one momentary force between them and the ball. Just for that split second during which the kick happens. The only force on the ball is the applied force. The only force on the person is another applied force of equal magnitude, opposite direction. They still don't end up moving the same way. They still don't get sent away from each other at equal speeds. And the reason is because of the mass. The reason is because of the mass. The person has more mass than the ball, so the person is going to end up with less acceleration. Even when they have the same net force exerted on them, the same magnitude of net force, they're still not going to have accelerations of equal magnitude because their masses are not the same. The more massive person is going to have less acceleration than the less massive ball. Pretty simple, straightforward. From there, you can figure out the math, throw in some numbers if you want to experiment with it a little, and give yourself a more concrete sense of it. But that's number 5. Equal and opposite forces do not mean equal and opposite motion. Number 6. Action and reaction always act on two separate objects. So sometimes a student will wonder, well, if we take corollary number 1, which says that the reaction always exists, and we know it's always equal and opposite, how come they never cancel out? How come all the forces in the universe never cancel each other out? It's because they don't act on the same object. So if I have, what can I use as a good example here? I mean, I can use pretty much anything. Actually, I could just reuse one of the ones I've already drawn. No need to waste more paper than necessary. Yeah, I guess we can go with this one. Well, actually, we can look at all of our previous examples. Yeah, let's work backwards through what we already have. So, over here, the person kicking the ball, whether it's the outer space scenario or the, on Earth scenario, either way, you notice that, let's say this is the action, the applied force on the ball. The reaction is not on the ball, it's on the person. If we look over here, action on the box, reaction on the person, or vice versa. Again, labeling action versus reaction is a completely arbitrary choice. Over here, the normal force exerted on the block, the reaction to it is the normal force exerted on the table. On the block versus on the table. Force of gravity on the block versus force of gravity on the earth. So always, 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 action and reaction act on two separate objects. And I guess this is just a repeat of what we had with the table. It doesn't matter if there's a table between them or if there's nothing between them. If it's a force of gravity, then one of them is going to be on the block and the other one is going to be on the planet or moon or star or whatever is exerting that gravitational force on it. So yeah, there you go. That's number 6. And finally, number 7, which I guess takes us back to the example that always bugs me. Number 7, action and reaction are always equal and opposite forces. But the converse of this is false. So even if two forces are equal in magnitude and opposite in direction, that doesn't mean necessarily that they are action and reaction. And I think this is the reason why this example that really bugs me exists out there in the world, because sometimes you have teachers or wannabe teachers that misunderstand this. So it is often the case that normal force and gravitational force on an object are equal. But the reason for that is because of Newton's second law, not because of Newton's third law. Again, net force equals mass times acceleration. So, in the case of this block, we know that its acceleration, at least its vertical acceleration, has to be 0. It doesn't accelerate up, it doesn't accelerate down. If it accelerated up, it would be levitating and lifting off like a rocket. We know that's not happening. And if it was accelerating down, it would be basically burrowing through the table, and we don't see that happening either. Or if there wasn't a table, if it was on the ground, it would be digging a hole into the ground. Again, something that we don't see happening. So that means that the vertical acceleration has to be 0, and the only way for that to happen is for the net force to be 0. So the reason that the normal force in this scenario is equal to the gravitational force is because it has to be. That's the only way for the forces up minus the forces down to be 0. If there was another person applying a force downward like this, for example, if I had somebody applying a force downward like this, well, then in this case the normal force wouldn't be equal to the gravitational force anymore. In this case, the normal force would actually have to be a little bit larger because, again, forces up minus forces down have to be 0. If the block is not accelerating up or down, then the upward forces must be balanced with the downward forces. So forces up, which is only the normal force, minus forces down, the gravitational force and the applied force, have to be 0, which means the magnitude of the normal force has to equal the sum of the magnitudes of the gravitational force and the applied force. And there you have it. So the reason that the normal force for an object resting on the ground is typically equal to the weight of the object in magnitude, it's not because of some sort of action-reaction relationship. Absolutely not the case. And yeah, I think that is all I have to say here. So, what else? Is there anything else? No, I think that's it. So remember these 7 rules. I'll put them up on the screen for you one last time so that you can see them in a sort of summary. And make sure you understand them. I mean, I guess I'll say memorize them, but really what I want you to do is understand them rather than memorize them. And remember the examples. I think the best way to remember these is to wait a few days after you've seen this video and just go back to the list itself, the list of the 7 corollaries, clarifications, again, whatever you want to call them, and see if you can come up with examples for each of them that illustrate the idea and illustrate the pitfalls and mistakes you could make from misunderstanding the idea. And yeah, I think that'll be it. So hopefully this has been helpful. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I will see you next time.